Hello, everyone. Welcome to Lattice Development Conference 2023. This session is all about deploying deep learning models in ultra-low power FPGAs. As you know, Lattice is a low-power programmable leader, and there are challenges around deploying AI models and coming up with the solutions. I think Lattice has been in AI for so the client space for 2022 onwards. So this topic is going to be, given by myself, Satish, and then Luke, and we have a partner, Taras from Plumarai. Let's get started. Next page. To introduce myself, I am Satish Chalappan. I'm a system architect at Lattice Semiconductors, looking at end-to-end system for client and IoT industries. I'm passionate about embedded imaging, audio, and high-speed areas. And now Luke will introduce. Go ahead, Luke.
Hello, everyone. I'm Luke Ge. I'm a AI engineer within the Lattice Semiconductor Application Group. My focus area is on designing, building, and optimizing AI solutions from training to inference, data center to edge, cloud to on-prem, covering different verticals like health, life science, IoT, cloud service providers, oil and gas, and academia.
Hi everyone, I'm Taras, co-founder and CTO of Plumarai, a startup making edge AI on different platforms. We are partnering with Lattice to provide tiny and efficient deep learning models on FPGAs. We support also other platforms.
Okay, in this section, I will first introduce some basics of deep learning, the overview, and the different stages in deep learning development pipeline. Then I'll deep dive into the challenges and show Lattice how Lattice addresses these challenges. The entire deep learning development pipeline involves three stages: data preparation, training, and inference. Let's take image classification as example. In stage 1, data preparation, we collect lots of images with one object on each image. Then we do the cleaning, set the correct resolution, and most importantly, label the data. That is telling what is on each image: butterfly, bicycle, strawberry. Data preparation can be very time consuming and labor intensive. It may take 70% of total time. In stage 2, training, as shown at the bottom, we train a model, which is a deep neural network, using prepared data in the first stage. In the center shows a 3-layered neural network example. The neural network contains a set of parameters called weights, denoted by W. The purpose of training is to find out the best set of weights W. During training, the dataset is firstly organized into multiple mini-batches. Each mini-batch contains a fixed number of images. The training involves many iterations. In each iteration, a mini-batch will pass through the neural network, layer by layer, from left to right, eventually generate an output called prediction. This is called forward propagation. At the beginning, when the model is not accurate, the weights W are just the random numbers. So usually there is a big difference between the prediction and the correct labels. The purpose of the training is to reduce the difference, which is done by backward propagation. The difference or loss is transmitted from backward from right to left, layer by layer, and eventually generate update delta W. Then the model can be updated with this delta W. WT plus 1, which represent the new model, equals WT, which is current model, plus delta W. The training process may involve millions of iterations. In each iteration, a mini batch passes the neural network twice, forward propagation, backward propagation, then generate a model update. Therefore, the model can be updated millions of times. Stage 3 is inference. Once we train an accurate model, we can deploy the model for inference. The input data goes through the model and generate accurate prediction. So inference is simpler. It only involves forward propagation. There's no backward propagation. Like other workloads, deep learning requires 3 basic resources: communication, memory, and compute. Next, let's take a closer look at these challenges on communication, memory, and compute. Model training involves many iterations. We can accelerate the model training by doing it in parallel. As this slide shows, on the top, we partition the dataset into 3 parts: blue, green, yellow. Then duplicate the neural network models on 3 nodes, 1, 2, 3. Each node hosts 1 copy of the model and processes its own part of data. These nodes are not running independently. Once a node processes a mini batch and calculates a model update, this update, delta W, needs to be broadcasted to other nodes. So here comes the first challenge: communication. How do we connect these nodes? What network topology we use? Scalability versus convergence. Let's look at the star topology at the bottom left. There is a parameter server in the center, surrounded by multiple workers. Each worker will calculate update delta W and send it to the parameter server. And the parameter server will do the averaging, calculate the model, and broadcast the new model to all the workers. So you can immediately see a bottleneck in the parameter server. It's an N-to-1 communication. It has very poor scalability. As the number of workers increases, this parameter server will get saturated, and it suffers slow convergence. The time complexity is O(n). Because the server needs to add up all the parameters sequentially. The only advantage of this topology is low cost. So it involves only n edges. So the cost of the network is very cheap. So that's why it's not very popular. It has been quickly replaced by the ring topology. In the ring topology, we can immediately see there's no bottleneck. It's very simple. Every node has only 2 ports, and it has very good scalability. You can easily add new nodes into the ring. The time complexity is the same as O(n), because each node has to transmit the update to the right neighboring node. It takes n hops to complete 1 circle. Also, the ring is very cheap. It only involves n edges. So then you may wonder, can we do the averaging faster? Then it comes to the butterfly. In butterfly, I show 4 nodes, and each node will calculate a unique update, delta W1 to 4. I use 4 different colors to represent that. So in round 1, every node will exchange the update with its nearest neighbor. So node 1, 2 will exchange. After that, they have the same information, so they become the same color, purple. And similarly, node 3 and 4 will exchange, and after round 1, they become the same color, blue. So you can see after one round, the number of colors is reduced by half. And in the second round of exchange, again, each node will exchange with the nearest neighbor of different color. So node 1, 2 will exchange with node 3 and 4. And the result is that all the nodes have the information and they become the same color. So you can see in butterfly, there is also no bottleneck. In each round, every node communicates with just one another node. So it's a one-to-one communication. Also, the time complexity is reduced to log n. The cost is more number of edges. It's increased to n log n. And you may wonder, can we do even faster? Then it comes to the fully connected topology. As you can see on the right, the time complexity is 0.1, so it takes only one step to update all the mode update to all the other nodes. But the price we paid is the high cost. Every node has n ports, and the number of edges is increased to n squared. So in summary, there is no single topology that can satisfy all. We must pick up the correct one based on our need, the constraints, the cost, the convergence rate. And Lattice FPGA offers reconfigurability to support various topologies, so it's very flexible. Next, let's look at the second challenge, memory. In deep learning, the neural networks usually contains many layers. These layers communicate through memory. One layer's output is next layer's input. Therefore, there's intensive data movement between the processor and the memory. Moving data back and forth can be very expensive in terms of power and time. Here shows how Lattice addresses the memory challenge. So from the throughput perspective, a naive method to reduce memory access is fusing operations together. So for example, we can fuse the ReLU layer with convolution, the convolution layer with batch normalization. In that way, we can reduce the communication between the layers. The second is pruning. Basically, we can reduce the number of layers, do some distilling, make the model smaller, shallower, and explore the sparsity so that we can also reduce the memory access. The second technique is called loop nest optimization. Let's take 2D convolution example. There are altogether 6 loops: the input channel, output channel, the image height, image width, and the kernel height, kernel width. So these 6 loops, we can change the order of them. So do some loop reordering. So that the innermost loop is a primitive that can exploit the underlying hardware. The third method we can explore is efficient memory hierarchy. Lattice FPGA has some embedded local block RAMs. These block RAMs are fast but small, so we can use them to restore repeatedly used weights. On the other hand, the FPGA has abundant IOs, and we can connect to some external hyper-RAMs. These hyper-RAMs are larger, so it can be used to store some intermediate results like feature maps. So in that way, we can greatly accelerate memory access speed. The other challenge is from the size perspective. We can do some techniques like quantization, convert the floating point FP32 numbers into integer 8 or bit 16. In that way, we can double or increase the memory throughput 4 times. Also, we can change the RGB colored image into gray image. In that way, we can reduce the image size to 1/3 of its size. And also we can reduce the image resolution and add more pooling layers, because after each pooling layer, the resolution is reduced. So we can reduce the memory usage. And also we can reduce the number of channels. Nowadays, in deep learning, the models are getting larger and larger. Sometimes it's impossible to fit a model into a single device. So we have to use a technique called model parallelism to fit a model into multiple devices. As this page shows, we partition the models. So device 1 will host 2 layers, layer 1 and 2, while device 2 hosts layer 3 and 4. A big difference between model parallelism and data parallelism, which was in the previous image, is that model parallelism will require very intensive communication between devices. In data parallelism, each node will compute its own data, process its own data independently. So during the forward propagation, backward propagation, there's no communication between the nodes. These nodes only communicate when update delta W is calculated. But in model parallelism, any data flow between these layers, either forward propagation or backward propagation, there's communication between these devices. So the bottleneck may shift from memory to communication again. Lastly, let's look at the third challenge, compute. Top left shows a typical deep learning neural network topology. The convolutional layer followed by batch normalization layer followed by pooling. There are 3 linear operations. 1 linear operation in convolutional layer, 2 linear operations in batch normalization. In the convolution, the input A multiplies the weight W, then adds the bias B. So this is 1 linear operation. And in the next layer, the batch normalization, the second linear operation normalizes the distribution to Z norm of mean 0 and variance 1. Every element in Z is subtracted by the mean mu, then divided by variance sigma. The third linear operation stretches Z norm to Z tilde of desired mean beta and the desired variance gamma. Once the training is complete, during the inference, we can accelerate the inference by fusing these 3 consecutive linear operations into 1 single linear operation. As the bottom left shows, Z tilde equals W tilde multiply A plus B tilde. This single linear operation is mathematically equivalent to the previous 3 linear operations. So by doing that, we can greatly reduce the computation. And also this optimization is lossless. There's no drop in accuracy. Lattice software also support lossy optimizations like quantization. We can convert to the FP32 parameters from single precision to int 8. And also we can do quantization during the training. I want to emphasize that quantization is lossy. So usually we can experience slight drop in model accuracy, usually within 1%. So far, I have talked about the 3 challenges in deep learning: compute, memory, and communication, and have shown how Lattice addresses these challenges. Next, I will let my colleague Satish to talk about the details of the actual deep learning solutions at the client side. Satish, the stage is yours.
Thanks, Luke. That was very clear how Lattice is solving those, in ultra low power FPGAs, right? So that's good. Now it's a good time, for folks who have any questions, please go ahead and put it in the Q&A widget chat box so that, you don't forget those questions, right? And we will try to answer those questions at the end of the presentation. Right? Okay. So with that, let's look at what are the challenges are at the system level. All right. Continuing with Luke's talk about AI model challenges in communication, memory, and compute. Right. So these challenges will expand when you're looking at end-to-end applications at a system level, and these can be applied to clients, servers, industrial, IoT, and multiple segments. Here, what I'm trying to show is an end-to-end system level application using a client example. On the top left is what you can see, a laptop lid where Lattice is developing solutions on ultra low power companion chip, doing offload of imaging solutions and saving power of the laptop battery. So this extends the battery life by 30 to 60 minutes in general. And some of these functions are shown here using cameras and in the future audio, and as well the T-Con, which is the timing controller used on the display side to reduce the panel brightness and save power. All these use cases use small and agile AI models that can do the inferencing. For example, the applications on the right side showing HPD stands for human presence detection, where you are looking for humans approaching the laptop, and then when the system is in sleep, it allows the SoC to completely shut down and save power, whereas the Lattice AI computer vision solution can look at the camera and do the inferencing and detect for the humans. Another application is the attention of the user, like if the user is paying attention to the screen. If not, it will dim the screen and reduce the power. The third application is onlooker detection. It's a more like a security kind of feature where if somebody is looking over your shoulders, then it would alert that a small pop-up message will come. The last one we are sharing here is the Face ID, which is like identifying the enrolled user. That means it allows for waking up the system only when a enrolled user or a authorized user is in front of the laptop, or on a continuous Face ID detection to identify that the authorized users are using the laptop. These are not authentication identification, but more like a identification to save power, and it offloads the SoC and save power at the end of the day. On the bottom left is what the progression of Lattice solutions. Started off with computer vision generation supporting one platform. That means you have a design that is tailored towards one platform. And in 2023 and 2024, Lattice is moving on to a solution where the same hardware can be deployed for multiple platforms. For example, an OEM could have a mid-range, a premium range laptops. These can be deployed into this. So not only in the client space, Lattice is involved in the industrial, automotives, and IoT sectors, where these models can be deployed on Lattice FPGAs. And how do we do that? Keeping the low power is using a technique very common in the industry called always-on island, which is a small portion of the chip that is running on an ultra-low power mode, and that manages the power of the rest of the FPGA fabric, and that becomes the the brain of the chip in terms of power savings. Right? On the right side, where we are showing the power delivery and management, it looks a little bit busy, but the idea is to show that the AI FPGA is using multiple inference from the rest of the system to save power. For example, on the SoC side, you have an interface to the USB, and that has its own low power options to save power. For example, if there is no communication with the SoC, then the USB can go into suspend mode or even disconnect and save power. And one other thing that we do in human presence detection is we turn off the FPGA for 90% of the time and then turn on for the 10% of the time and do the human inferencing. And the FPGA itself has, the aux power and the core power, and these two power rails are managed. And the power rail for the main fabric is managed by the always on, and the FPGA also can control the power of the camera, which we do that, to save power, because cameras by itself is a very high power if you're running at 30 FPS and so. But when you're running human presence detection, we run it at 1 FPS, in the range of 1 FPS. And the camera PMIC, which is the power management IC, is also controlled by the FPGA. A closer look at some of the new the announcements coming from Lattice is the new Crosslink NX33U. This is the U stands for ultra low power, or you could say the USB, which is introduced first time, right? And it has the same concept of the low power island, which has some timers that does the wake function, or it can do a GPIO wake as well. And there are programmable GPIOs that are typical in Lattice FPGAs. And the bulk of the fabric is the center portion where all the logic sits in there, right? And these FPGAs, all FPGAs in general support bitstream encryption and authentication, right? And which is core to what Luke was talking about. The AI models are manageable, but the security aspect of it is very, very important, where we want to make sure these models, including the RISC-V core, are secure, and it's not tampered. USB 2 and USB 3 is a new interface that's been added to Lattice FPGAs. These are hard IP blocks that are available in this chip, and it doesn't consume any of the fabric space, so that's an advantage. And USB is pretty common in any systems, doing control functions or doing streaming functions, right? And the new Crosslink NX33U has an instant on function with 3 milliseconds of IO configuration and 8 to almost like 15 milliseconds of the FPGA device configuration. And these AI models, the challenges of AI model, one of the challenges is to map all the functions. And when you are going to ultra low power FPGAs, all the low level primitives are not mapped fully into the ultra low power FPGA. So there is a companion compute that is available on the chip, for example, an MCU or a RISC-V core, and these provide an offload function for those complex compute that are not mapped into the machine learning engine, right? And the RISC-V firmware itself is a very scalable and configurable architecture. This shows the firmware stack, and at a high level, you have multiple models, right? Like you could have multiple use cases running in the FPGA at the same time on a time shared fashion. And that's one of the things that Luke was talking about is, you have multiple models shared across single FPGA, or you could have single model shared across multiple FPGAs. And these compute functions manage the power as well. It manages the authentication, the SPI flash programming, and the rest of the infrastructure. And these stacks are modular in such a way that if some of the functions are not used, then these can be disabled and save both code and memory space on the chip. On the bottom left is what we are showing here is the typical SPI flash contents, and you can see the contents completely adds up, right? So you have the flash management design, which is used as a golden to do the golden is a concept where if for some reason if the FPGA or the design is corrupted, then you can fall back onto this golden design to go into the recovery mode and still be functional, right? And you have the RISC-V core and the AI models, and there are some protected regions that could store some flags in terms of biometrics or some kind of anything related to the AI model as well, right? And there are current version and the golden version of these images. And one of the good things about FPGAs in general is reprogrammable. But the concept is it can be the firmware and the AI models can be updated over the air. So that gives an extra advantage, right? And these can be updated through Windows Update, through regular Microsoft Windows or any other OS that you are working with, right? And one of the protocol that Lattice has adopted is component firmware update. This is a inbox open source protocol, and Lattice has adopted it, tuned to to the system. For example, this same protocol can be used to update the firmware for one FPGA or multiple FPGAs in the system, right? Because if you remember, one of the system level views had one FPGA for audio and the other FPGA for imaging. And here, this ladder diagram shows a very high level view of the camera, the FPGA, and and the some bridge, for example, an Intel or a AMD bridge in the between, and the actual CFU host drivers, and the Microsoft Windows Update. And they have a protocol to check the version and look at when is the right time to update, because when you are in active imaging function, you don't want to compromise on those bandwidth and all those things. So the firmware update is triggered when there is an idle time and when the versions are outdated, right? And these are all happening as part of the regular Windows Update, so there is no major involved. So so let's move on to the next concept of system power flows, because deploying AI model is one thing, but then meeting the power performance and the and the latency goal of the system is very, very important. In typical systems, you could have a system state like S0 is an active state. Modern connected standby is like a S0IX, like a deeper low power state of S0. And there could be S3 as in sleep and S4 as in hibernate. In all these states, the FPGA needs to transition in and out, either enabling the AI function or disabling the AI function. Here it just shows a typical client use cases where the system is going inactive and then going into sleep. For example, S0 is an active state and MCS is a sleep state, where the USB, the AI function, the camera, the GPIOs that is talking to the sensor hub, and all the power gated domains are working in tandem fashion. And this slide talks about the different contributors to the power, right? For example, in S0IX, you have the baseline system SoC power that is outside of our control, but that's also included in the overall system. The sensor power is a major contributor. That's also a baseline that's outside the scope of Lattice FPGAs. And in the computer vision or in audio FPGA, in any AI function, you have a contributor and there is a target that we need to meet. And that's an example of a target that's shown here for the human presence detection. Okay. And the same thing on the bar chart on the bottom histogram. What we are showing is a progressive power adder that each component is adding, coming to an overall system power of 45 milliwatt in a human presence detection. Right? And on the top right is where typical contributors showing where there could be one or more camera sensors like RGB, IR, that's communicating through MIPI CSI interface, or even sometimes USB, and then interfacing on the through the hinge to the SoC, either USB or MIPI interface. So FPGA becomes a major contributor to the power, and the baseline power is on the number 3, which is the SoC. And these solutions, deep learning models, involves a balance between memory and compute that Luke was talking about. And these memory and compute, are balanced by putting these models and the firmware in a layered hierarchical fashion. For example, SPI flash could be a far memory like an L3 memory, and the fabric large LRAMs could be an L1 memory, and there could be a cache that is closer to the RISC-V core or to the ML engine. They could be caches like L1 caches and stuff like that. And these balanced hierarchical network architecture gives us an ability to break down the model if it's a large model, or even sometimes race to halt, run the model fast, and then save power. Right. So it's a compromise between the applications. Power savings and management, and that's very important, right? So the model being by itself low power doesn't give a lot of advantage at the platform level. You need to manage the overall power, for example, lowering the power of the USBs, and power gating and clock gating the design in general, right? And as I showed you, the power gating of the major of the fabric is done by the always-on engine, but there are other techniques that Lattice solution employs in terms of clock gating, fine-grained clock gatings, and saving the dynamic power, right? And the overall architecture is what a Lattice advantage comes in picture. There on the bottom right is what we are showing here is a variance of power saving techniques. If you don't choose an always on, if you don't choose an FPGA device with an always on, in that case, a smaller FPGA like an ICE40 could be used as a power manager that manages a bigger FPGA like an NX40 or even Cetus Pro 100, right? So that means you have a big little architecture where the smaller FPGA is managing the power for the larger FPGA based on the use case. For example, you don't need to be constantly running when you're doing human presence detection. So these can be taken care. Now with that, I hand over to Teres from Plumerai to talk about an exciting use case that he's working on, collaborating with Lattice. Go ahead, Teres. Take over, please.
So we have partnered with Lattice to create a new and very exciting, at least for me, use case to combine embedded edge AI with FPGA and a high-resolution video streaming. So we have prepared a smart monitor for teleconferencing. The device, full-stack device that can track people positions, choose the best zoom ratio. It can automatically detect one or several persons in front of the camera, choose a proper zoom in with nice cinematographic changes between scenes, implement background in the blurring or replacement, and detect people's faces for further image enhancement. Also estimate user head pose for an additional enhanced functionality for the teleconferencing. It must also have several features to be useful. First of all, it should work with the standard USB video class functionality. It supports by many operating systems So in order to quickly integrate it into our existing system, we must support that. It should support one person or several people in the frame, automatically detect their position. And it should work fast enough because people can move, people can rock on the chair, people can come into the frame and come out of the frame, but still allow some hysteresis so the image will not be shaking that much. Next slide, please. So let's start with the hardware we use for that. For that demo, we have used Certus Pro VVML, it's voice and vision machine learning board, with Sony IMX258 camera connected. For this use case, we have used QSPI memory, HyperRAM, and Cypress FX3 USB chip as a peripherals available on that board. How does it work? Sony IMX258 camera, it's a great sensor, but it lacks any ISP functionality. So we had to put ISP also inside the FPGA. We have used the advantage of hard and MIPI channels on Certus Pro to capture the high-resolution video stream from the camera, process it with the ISP, standard automatic white balance, standard debayering, and other algorithms to improve the image quality. After that, smart, controlled by AI, two-dimensional video scaler chooses the best crop and zoom parameters for the given frame. After that, depends on the use case, whether we're just using auto framing or whether we want to use also some background blurring replacement. We either perform that background masking and then replacement of blurring, or we simply reduce the image with the auto framing. Then convert it to UIV 422 format, so required by USB video class standard, and stream it in a full HD resolution to the host. To control that quite sophisticated video and AI pipeline, we have used a RISC-V SoC soft-core processor, also embedded in the FPGA. The main challenges of the design, and it's hard to say main because there are several important challenges. First of all, we are processing video in hard real time. Despite we have HyperRAM memory on the board, its bandwidth is not sufficient to process and to receive and transmit full HD high resolution video in real time. So we must do all the transformation within one frame. Another challenge is that we must run one or several neural networks. In the very basic functionality for auto framing, we just need some face detection or body detection. When we want to do background blurring, we need first to perform a scene segmentation, so to determine which parts of the image belong to the people and which parts are background. And then if we want to also do blurring, we can also perform blurring via 2D convolution, and we also can use our CNN engine for that. The models AI models to perform those functions, they are quite big, quite large. They will not fit into FPGA, so we have to store it in some external memory. Also, we would like to have instant on functionality, so the demo case should work after powering up the board without reprogramming it all the time. So we have to put, of course, a bit stream, the firmware for our RISC-V processor, the models into an SPI flash, and make it available to the system. Quickly, we understood that just as the SPI interface speed, it will be a bottleneck. So we have implemented our own QSPI master and connected it to our RISC-V SoC. Another challenge was the bandwidth of the video itself inside the FPGA. So the best way to manage to reduce the amount of data passing was to convert the video to UIV as soon as possible, because UIV uses only 2/3 of bandwidth compared to RGB 888. And also do that cropping reduction also as early as possible. For image quality, we have experimentally determined that the best to accept 4K stream from the camera, and after that crop it to the full HD video. For the AI functions, we don't need that high resolution. We can simply work on QVGA resolutions and lower. So we have created a parallel video pipeline with a hyperram in the loop. Hyperram performs quite well when storing that low resolution video, and the CNN accelerator access patterns actually favor to store intermediate video frames in the hyperram. Hyperram also is serving as a main system memory for SoC. It's also a shared memory between a CNN accelerator and a RISC-V processor. So the inference results, like the video mask or facial pose features, 3D head pose features, they are shared with a RISC-V processor via hyperram. Processor also takes care of the neural network post-processing, like non-maximum suppression for face detection, or mask healing for background blurring, because sometimes the inference result gives some holes in the mask that will look bad in the scenario. Another challenge was that with using FX Cypress, or now it's Infineon FX3 chip, we found that it's quite sensitive to the streaming speed on the parallel interface. Any kind of hiccup, any kind of buffering inside the FPGA caused UVC video stream to be broken, and then we had some lags on the host platform. We have successfully also solved that by optimizing our clocking domains inside the FPGA. And last but not the least, we have implemented also UVC metadata according to the UVC metadata standard to pass useful information to the host. For example, number of people present on the screen, facial features, coordinates, and other useful information. Also, a USB FX3 chip is used as to create a backward channel of communication from the host to the FPGA. We use that channel, for example, to replace the background image. Overall, we have created, I believe we created very versatile and useful demo case. So the main challenges of that project was first the image quality, and balancing that image quality and the bandwidth that can be handled by the FPGA, by the AI, and by the Infineon FX3 chip. Experimentally, we have determined that it's best to capture the 4K resolution from the camera, and after that, a crop full or and zoom full HD video out of that 4K. Also, we had to work in hard real time. The hyperram bandwidth is insufficient for the full HD video streaming, so we had to, all the processing had to be done within one frame time. And we had to run multiple AI models on the same frame. Luckily, none of those models required high resolution video. They were all working in QVGA and lower resolutions. So we have created a parallel video pipeline with hyperram in the loop. For background segmentation, for pose estimation, and for blurring, we were able to sufficiently use hyperram, and after that upscale as a necessary the blurred and masked background image back to the full HD without much loss of the quality. As a result of the project, I believe we have created very versatile and feature-rich team. So in one project, you have 4K to Full HD video streaming, full HD ISP functionality with very high image quality, AI-controlled image rescaling on the fly, very smooth pan and zoom, video stream blending and masking also in Full HD, background segmentation, face detection, and head pose estimation, all done on the same CNN engine running in the FPGA, inside the FPGA, and with post-processing done on the RISC-V processor, also embedded in the FPGA. Also, we have created a very nice RISC-V SoC optimized for that AI functions with high-speed QSPI flash master support. With models and the bitstream and the firmware all placed in the QSPI flash and executed straight from it without copy. That gives us great boot time. Basically, after powering the board within milliseconds, it can start providing you the video inferencing on the fly.
Thanks, Taras. It was an exciting collaboration with Plumerai and Lattice, and we are looking forward to deploying into the market, right? And to summarize, how to deploy deep learning into ultra low power FPGAs. The key is still the power, the cost, and the flexibility, and still meet the performance of the AI functions, and keep the power as low as possible, and and have the communication with the rest of the system. For example, talking to the SoC, talking to the sensors, the high speed, low speed communication, everything. And the memory challenges that Taras and Luke was talking about, we still need to solve those things to deploy at a system level. And the compute, there are challenges with ultra low power. You can only achieve certain things. So in that scenarios, the model is optimized a little bit, and then the power is consumed. And we do some concepts like race to halt, big little architectures where you have hierarchical AI models to meet the overall power goal. So with that, we will move on to the Q&A session. So there are a few questions in the chat. Let's take a look at it. Luke, there are a couple of questions. You can go ahead.
Okay, the first question I received is, what is the max clock frequency achieved in typical FPGA? And how does it affect AI functions? So for the clock rate, it depends on several factors. First is the manufacturing process. The later FPGAs based on the neural process can achieve high clock rate, typically 300, 400 megahertz. The other factor is based on the size of the model. If the model is very small and there are abundant resources to place and route the design, then the clock rate is higher. If the model is very large, uses nearly all of the resources, so it's very challenging to do the placement route, and then the clock rate is lower. The clock rate actually affects AI functions. The first is the latency. It decides how fast the system will respond to input. So it's very important to the real-time applications. The second is on the throughput. For computer vision tasks, it's like the frame per second. The second question is, what is the method to achieve large models? So the first method is do some optimization during the training. We can exploit the sparsity of the model. For example, to do some pruning, some fusions, to reduce the network layers, make it shallower, smaller. The second is to reduce the weights. The weights during after training are usually floating point single precision numbers. We can quantize these weights into 8-bit. So in that way, we can greatly reduce the size. The third method is do some model parallelism. If the model is really large, we can partition the model into multiple parts and fit it on several FPGA chips. But the one potential challenge is that the bottleneck may shift from compute memory to communication.
Oh, I see the next question. I can take that one. The question is, what are the challenges in IoT system architecture? So yeah, that's a very good question. So the challenges between client space and IoT and automobile vastly changes because the targets are different. For example, client on a battery powered system, they are targeting towards low power. But if you're looking at in industrial or automobile, generally they are powered through Ethernet or some wall adapters. So the power is not a main challenge. Generally, typically in IoT systems, the challenges that we see is to balance the multiple use cases by deploying multiple models. So these run at a different frame rate. So that means there are some functions that rarely runs, and there are some functions that constantly runs at a very fast rate. So balancing these models and then keeping the memory in check by fetching the models and then executing them and then fetching the model 2. And I would say the model management and memory management is a challenge. And Lattice solution, the solution that Luke and Taras and myself put together gives overall picture of that. I see the second question as well. I can take that one as well. The question is, does over-the-air update supported on Linux as well? Right? Yes, that's correct. The one of the architecture that we presented was the component firmware update. This is an inbox supported both on Windows as well as Linux. On Linux, we go through the Linux vendor firmware update. So that's typical in terms of Linux kernel update, where if you're in the systems, and then if you have registered your system into the library, then you pretty much have a node where you can go and update those things. So yes, the component firmware update is transparent. So that means the Lattice solution on the node side remains the same, whether the host side is Windows or Linux. I see the next question that Taras can address. Please go ahead.
So how are those AI models protected, and how big those models are? So maybe I can combine the answer for both questions. So for the face detection model is roughly 700 kilobytes. The scene segmentation model is roughly over 1 megabyte. The models are compiled using Lattice neural network compiler. So the output format is already encrypted and can be understood only by the encrypted CNN IP engine. So we are combining those models together with the bitstream to program the QSPI flash. So it has the same level of encryption as your bitstream for the FPGA. And the QSPI flash memory size was not an issue for that project.
Thank you. With that, we conclude our Q&A session, and we hope you enjoy the rest of your time at the Lattice Developer Conference 2023. Thank you very much.